Hello class, welcome back to Physics for Engineers, and this is the 10th module of our course, and our topic for today is fluids. So by the end of this module, the student is expected to learn about number 1, mass density, specific gravity, pressure, and atmospheric pressure. Number 2, gauge pressure and absolute pressures. Number 3, characteristics of fluids and at rest and in motion. Number 4, buoyant force on an object immersed in a fluid. Number 5, pressure and flow speed of a fluid at any point in a flow tube. And number 6, Archimedes, Bernoulli's principles, as well as the Rosselli's theorem, Windsor's principle, and Poiseuille's law. So let's start with fluid statics. So if in mechanics we have the statics of rigid bodies and dynamics of rigid bodies. Well, in fluids we also have the fluid statics and fluid dynamics. So basically, fluid statics is the study of fluids at rest. So let's start with the basics. First, mass density and specific gravity. So I know you're already familiar with density and specific gravity, but anyway, the mass density of a material is its mass per unit volume, which is equal to rho is equal to m over v. So the specific gravity of a substance is the ratio of its density to the density of some standard substance. The substance is usually water at 4 degrees Celsius for liquids and solids, and for gases it is usually air. So the general formula for specific gravity is this: Sg is equal to rho over rho standard, or the density of your substance divided by the density of your standard, which is water or air. Okay, so pressure is the amount of force divided by the area it is exerted on. So we have already touched this topic in elasticity, I guess. So in our discussion for today, we assume that the pressure is always normal pressure, or the pressure is exerted on a perpendicular plane. So the average pressure is defined as the force acting normal to the area all over the area over which the force is distributed. Now, if the force varies over an area, for example, the area is not a perfectly flat plane, or the force is not consistent over the area, well, the pressure, this should be dP, but anyways, pressure is equal to the differential force over the differential area. So the standard atmospheric pressure is the pressure that is exerted upon us by the atmosphere of the Earth. So even though the gas, we think that air is weightless, right? But if we think about it, there is a thick layer of air surrounding the Earth. So that thick layer of air must have some weight. So that weight is the pressure that we feel, the atmospheric pressure that we feel while living on the surface of Earth. So that standard atmospheric pressure at sea level is 1.01 times 10 raised to 5 kilopascals, or 101.325 kilopascals, which is equivalent to 14.7 pounds per square inch, or 14.7 psi. So this value is assumed to be standard, but in reality, the pressure of the air, the atmospheric pressure, varies with the location. So some locations are above sea level. So if the location is above sea level, therefore there is less air above that location. So the pressure is less. But some areas are below sea level, so there is a thicker layer of air above that location. So the pressure there is more than this atmospheric pressure, but it is assumed that anywhere this is the standard atmospheric pressure. So this value is also equal to 1 atmosphere is equal to 1.013 times 10 raised to 5 pascals, or as I said, 101.325 kilopascals, which is also equal to 760 millimeters of mercury. So we will discuss this later on, this 760 mmHg. So 1 Torricelli or 1 millimeter of mercury on the barometer, 1 mmHg, is equal to 133.32 pascals. And 1 psi, so you can see this unit psi in automotives or in bicycles. So 1 psi, the English unit for pressure, is equal to 6.895 kilopascals. So psi is short for pounds, and this is pounds per square inch. Okay, so let us differentiate gauge pressure and absolute pressure. So when we say gauge pressure, it is the barometric pressure, or the pressure as read from a gauge, from a pressure gauge or from a barometer. Now absolute pressure is the amount of the atmospheric pressure plus the pressure on the gauge or the barometer. So how did these terms come about? Now, one instrument used to measure atmospheric pressure is the common barometer, invented by Evangelista Torricelli in 1608, who was born in 1608 and died in 1647. So this is the picture, and this figure is the schematic diagram of a common barometer. So as you can see, this is a common container of liquid. Then there is a tube that is submerged partially, and this tube contains this liquid also. And at the tip of that tube there is a small gap, but that small gap is supposedly vacuum, so the pressure there is supposedly zero. So yeah, the close end of the tube is nearly a vacuum, so the pressure at the top of the mercury column can be taken as zero. So the pressure at point A, this point, due to the column of mercury, must be equal to the pressure at point B due to the atmosphere. So you can recall this principle from your high school physics. So in your high school physics, it is said that the pressure at any level, the pressure at the same level for for the same fluid should remain the same, right? So the pressure at point A, due to the column of mercury, since they're the same fluid, must be equal to the pressure at point B, and the pressure at point B is due to the atmosphere. So if that were not the case, there would be a net force that would move the mercury from one point to the another until the equilibrium is established. But since there should be no motion, so the liquid here is not going down or up, and the liquid here is not going down or up, then this must be in equilibrium. Therefore, the pressure exerted by the liquid here at point A is equal to the pressure exerted by the atmosphere here at point B. Therefore, this formula can be derived from the formula pressure is equal to rho GH, so density of the fluid times gravitational acceleration times the height of the column is equal to the pressure. But since we are looking for the height of the mercury column, we have already derived the formula. So H is equal to PO over rho HGG. Sorry, this should be the one that we discussed first. So PO, or the pressure at point O, is equal to rho Hg, the density of mercury, times G times the column of the mercury. So going back, the pressure at point O should be atmospheric because it's open to the air. So the atmospheric pressure is 1.013 times 10 raised to 5 pascals all over 13.6 times 10 raised to 3. That is the density of your mercury. times g, which is 9.8 meters per second squared. So please don't use this when doing your calculations during exams or quizzes. We use 9.81, not 9.80. I think I just followed the book or something. I just made a typo error, I think. So anyway, our answer should be 760.760 meter or 760 millimeters of mercury, and that tallies to this value. So the atmospheric pressure is equal to 760 millimeters of mercury on a Torricelli barometer. Okay, so let's have another example. Okay, so suppose that Blaise Pascal duplicated the Torricelli's barometer using a red Bordeaux, I don't know how to pronounce this, Bordeaux wine, using a red Bordeaux wine of density 984 kilograms per cubic meter as the working fluid. What is the height h of the wine column for normal atmospheric pressure? So let's just do what we did earlier. H is equal to PO rho, this should not be HG, rho wine G is equal to the PO or atmospheric pressure is 1.013 times 10 raised to 5 all over 0.984 times 10 raised to 3, which is your density. I just changed it into a scientific notation, kilogram per cubic meter times 9.81 meters per second squared. Now we get 10.49 meters. That means that we need 10.49 meters of wine to duplicate this Torricelli barometer. Okay, so let's try something harder. Well, in this problem, mercury is poured into a U-tube shown as below. So as you can see, this is the U-tube and both ends are open. So that means in this point and in this point, the pressure is both atmospheric. The left arm of the tube, this one, has a cross-sectional area of 10 centimeters squared, and the right arm has a cross-sectional area of 5 centimeters squared. 100 grams of water are then poured into the right arm as shown, this one. So we pour 100 grams of water here. Determine the length of the water column in the right arm of the U-tube, and given the density of mercury is 13.6 grams per cubic meter, what distance h does the mercury rise in the left arm? Okay, let's give it a try. So first, let's determine the length of water column in the right arm of the U-tube. So if you can observe, this left arm, this right arm of the U-tube is in the shape of a cylinder. So don't mind this. We should assume that the water will not go on the curved part of that thing. So that's because it would make things more complicated. So since we already have the mass of the water, and we know the density of the water, and we know the cross-sectional area of this one, therefore we can get the volume and we can get the height of your water column. So how much cubic meters is 100? How much water did we just pour? How much cubic meters did we just pour into this arm of the U-tube? So V is equal to area of the base times height, or cross-sectional area times height, but V is also equal to m over rho. So this formula is from the formula of density. Rho is equal to m over V. So we know that we poured 100 grams of water, that is 0.01 kilograms all over 1000 kilograms per cubic meter. So solving this, we get 1 times 10 raised to negative 4 cubic meters. That means we poured this much water. 1 times 10 raised to negative 4, or 0.0001. 3 zeros before 1 cubic meters. Now, how high is that? H is equal to, I cross multiply this, I put this A below B. So H is equal to 1 times 10 raised to negative 4 cubic meter all over 5 centimeters squared times 1 over 100 squared. I just converted this 5 into cubic meters. So 1 over 5, 1 times 10 raised to negative 4 over 5 over 10 squared, 100 squared. So we get 0.2 meters or 20 centimeters. That means that this water is 20 centimeters high. Okay? Now, proceeding to our next question. Given that the density of mercury is 13.6 grams per cubic meter, what distance h does the mercury rise on the left arm? Now, this is a little more complicated, right? But I think we can solve this with our given, with the data that we are given. So, if you can observe here, when we poured water, the mercury here was displaced, right? So it's displaced, and some of the mercury of overflowed from this line. Okay, so the mercury was displaced, and but the amount of mercury in this YouTube manometer still stays the same. So that means that the amount of the amount of mercury displaced, this is H, so the cross-sectional A1 times H, this is the amount of displaced mercury, is equal to A2H2, or is equal to this amount. So I think you can understand that. So mercury was initially here. So when we poured water, the mercury was pushed to this line, and it was this line, this level of mercury has risen up. It rised up. So this volume is equal to this volume. Okay, so taking the pressure at this line, so I drew a line here, the line on the interface between the water and the mercury, because practically they don't mix. So at this point, the pressure here is equal to PO, or P0, or the atmospheric pressure at A2, plus the pressure exerted by the water column. So that is PO plus rho GH of the water. Now, from the left side of the manometer, the pressure at this line is equal to the pressure exerted by this column of mercury. So that will be rho GH plus H plus 2. So rho GH plus H plus 2 plus the atmospheric pressure PO. So if we equate the two equations, because they're both equal to the pressure at line 1, PO is equal to PO plus rho GH plus H2 for the left side is equal to PO plus rho GH of the water. So we can cancel out PO, and we can also cancel out G. So what remains will be this equation, rho G H plus H2. So don't mind the G, I just forgot to delete that. So rho G H plus H plus H2 is equal to rho GH of the water. Now, if you can remember, H2 from here, we don't know H2, right? But we don't have to get that value. So let's express H2 in terms of A1 and A2. So H2 is equally A1H over A2. So substituting that here, we get H plus A1 over A2H, but I regrouped that expression into this. So rho HGH times 1 plus A1 over A2, because they both have H plus HA1 over A2. is equal to rho WHW. Okay, now if I manipulate this equation more, I can finally derive the formula for H. So H is equal to rho WHW over rho HG1 plus 1 plus A1 over A2. So substituting the knowns to get the unknown H, we get 1000 times 1000 times 0.2 over 13,600 times 1 plus 10 over 5. So why did I not convert 10 centimeters squared and 5 centimeters squared into meters squared? Because they're both centimeters squared and I'm just gonna cancel it anyway. So this becomes unitless. So the units does not matter at all. So finally, our answer is 0.0049 meters or 4.9 millimeters or 4.49 centimeter or half a centimeter, if you may. So let's go back to our let's discuss the rest for gauge pressure and absolute pressure. So a device for measuring the pressure of a gas contained in a vessel is the open tube manometer. One end of a U-tube shape containing a liquid is open to the atmosphere and the other end is connected to a container of a gas at pressure P. So basically this manometer is just like this one. This is the U-tube manometer. This is a form of the manometer that is used for measuring the pressure of the gas contained in the vessel. So one end of the U-shaped manometer is exposed to the gas inside a vessel, while the other end is exposed to the atmosphere. And in an equilibrium situation, the pressures at point A and B must be the same. So the pressure at point A and point B must be the same if they're on the same level, because they're the same fluid. Otherwise, the curved portion of the liquid would experience a net force and would accelerate. And the pressure at A is the unknown pressure of the gas. The difference in the pressures is equal to rho GH. The pressure P is also called the absolute pressure, and the pressure difference P minus PO is also called the gauge pressure. So that's another way of defining absolute and gauge pressures. Now let's discuss the Pascal's principle. So because the pressure in the fluid depends on the depth and the value of PO, the n increase in the pressure in the surface must be transmitted to every other point in the fluid. This concept was first recognized by the French scientist Blaise Pascal and is called the Pascal's law. A change in the pressure applied to a fluid is transmitted and diminished to every point of the fluid and to the walls of the container. Now, the most common application of this principle is shown in this figure. So this is the I think this is a car jack. Sorry, it's not a car jack. I forgot what this is called, but this is the device where you step on a small area, then that small area presses a fluid, which in turn exerts a pressure in this bigger area. And because of Pascal's principle, that bigger area and because pressure is transmitted and diminished to every point of the fluid, therefore there is a bigger amount of force is transmitted to the other end, so it pushes the car. Because the increase in the pressure is the same on two sides, a small force on the left produces a much greater force at the right. So remember the formula for pressure. Pressure is equal to force over area. So if the pressure on the right is equal to the pressure at the left, Therefore, F1 over A1 is equal to F2 over A2. So, um, they don't have the same, they have the same amount of pressure. So therefore, for a smaller area and a smaller force, it can produce a bigger force at a bigger area. So let's have some examples to understand Pascal's principle more. So, in our example, estimate the force exerted on your eardrum due to the water when you are swimming at the bottom of a pool that is 5 meters deep. So, suppose that your head is at the very bottom of that pool and the pool is 5 meters. Let's estimate the surface area of the eardrum to be approximately 1 centimeter squared, or 1 times 10 raised to negative 4 meters squared. So, the bottom of the pressure at the bottom of the swimming pool is equal to atmospheric pressure plus rho GH. So that means that the difference between the pressure at the bottom and the atmospheric pressure, or basically this is the gauge pressure, P bottom minus PO, is equal to rho GH 1000 times 9.81 times 5. So that will be equal to 49,050 pascals. Now, how much force does this pressure exert on your eardrum if your eardrum is 1 centimeter squared? So force is equal to pressure times area. So 49,050 pascals times 1 times 10 raised to negative 4 is equal to 4.905 newtons, approximately 5 newtons on your ears. That's a little painful and uncomfortable. Okay. So, let's discuss Archimedes' principle. So, Archimedes' principle deals with buoyancy or buoyant forces. It states that the magnitude of the buoyant force on an object always equals the weight of the fluid displaced by the object. So, suppose I have a beach ball here, and at the same time I have a parcel of water here. Let's say this is a container, a plastic container, and it contains the water that is the same water as this surrounding fluid. So the buoyant force on a beach ball that replaces this parcel of water is exactly the same as the buoyant force on the parcel. So because the parcel is in equilibrium, there must be an upward force that balances the downward gravitational force on the parcel. So this is our parcel. So of course it has weight Fg. But because of the buoyant force, because we assume that this is in equilibrium, therefore the buoyant force is equal to the weight of this parcel. So this upward force is called the buoyant force, and its magnitude is equal to the weight of the water in the parcel. The buoyant force is the resultant force on the parcel due to all forces applied by the fluid surrounding the parcel. So suppose that we replace that parcel with the beach ball. So a beach ball contains water, right? So and when you press the beach ball at if you submerge the beach ball on the water, you can feel an upward force. So that force is your buoyant force, and it is equal to the amount of water, the weight of the water displaced by the beach ball. So I have another example here. Suppose it is a cube. Why did we choose a cube? Because it is easier to obtain the volume of a cube. So it says that the buoyant force on the cube is the resultant of the forces exerted on its top and bottom faces by the liquid. So since we said that buoyant force is equal to the weight of the water displaced, therefore buoyant force is equal to the pressure at the bottom minus pressure at the top of the cube times the area there exposed to the fluid, which is equal to rho GHA. So since H times A is equal to the volume. Therefore, the buoyant force is equal to rho, or the density of the fluid, times the gravitational acceleration g, times the volume displaced. So we have two cases for submerged objects. We have the totally submerged object and the floating object. So when an object is totally submerged in a fluid with density rho, the volume V of the displaced fluid is equal to the volume of the object. So remember, the volume of the displaced fluid is equal to the volume of the object for a totally submerged object. The magnitude of the upward buoyant force is B is equal to rho fluid G times volume of the object. So we have two cases here for the totally submerged object. One is, this is wood, so you can assume that wood has a tendency to float. And the other is metal. So metal is dense, so it has a tendency to sink. So in this case, the rho, or the density of the object, is less than that of the fluid, while in case B, the density of the object is greater than that of the fluid. So a totally submerged object that is less dense than the fluid in which it is submerged experiences net upward force and rises to the surface after it is released, while a totally submerged object that is denser than the fluid experiences a net downward force and sinks. Okay, but we assume that the object stays stationary in these two examples. So how about case 2? The case of the floating object, like the example A here. So in the case of the floating object, the fraction of the volume of a floating object that is below the fluid surface is equal to the ratio of the density of the object to that of the fluid. So basically, you just take into account the amount of the portion of the object that is submerged in water. So you won't care about this part which is not submerged in water, because it does not displace fluid, so there is no buoyant force there. So V displaced over V object is equal to rho object over rho fluid. So because the object floats in equilibrium, rho is equal to Fg. Okay, so let us have an example. So this is a popular tale in science. This is where this is the tale where Archimedes finally solved the problem given by the king when he was in the bathtub, and he just went out of the streets naked, yelling Eureka. But anyway, this is let us try to solve the problem that was given to Archimedes by the king during his time. So Archimedes supposedly was asked to determine whether a crown made for the king was consisted of pure gold. According to legend, he solved this problem by weighing the crown first in air, then in water, as shown. Suppose the scale read 7.84 newtons when the crown was on air, and 6.84 newtons when it was in water. What should Archimedes have told the king? So first, let us do some summation of forces here. So in case 1, summation of forces is T1 minus Fg is equal to 0. And in case 2, T2 minus B plus B minus Fg is equal to 0 also. Okay. So in case 2, we have an additional force, which is the buoyant force, which pushes the crown upward. So we come up with two equations for equilibrium, which is for buoyant force. Buoyant force is equal to Fg minus T2 from this equation, this part of the equation. And we know that this buoyant force is equal to rho water, density of water times G, times volume of the crown, or equal to the volume displaced by the crown. So from the density of the crown is M over V, which is rho C is equal to MC over VC. And if we multiply G both at the numerator and the denominator, so why did we do this? So that we can replace this value with something related to buoyancy. So VCG, so if you notice, if we take out this part of the equation, then put it at the bottom of B, so we get B over rho W, which is equal to VCG, MCG over B over rho W, which gives us MCG rho W over B. But since B is equal to Fg minus T2, therefore the density of the crown is MCG rho W over Fg minus T2. Substituting, you have 7.84 times 1000 over 7.84 minus 6.84, which is equal to 7.84 times 10 raised to 3 meters per 7.84 times 10 raised to 3 kilograms per cubic meter. So therefore, the density of pure gold is 19.3 times 10 raised to 3 kilograms per cubic meter, which is very far from the value that we obtained. Thus, the crown is not pure gold. So that will be all for today. The next part of this module will be about fluids in motion or fluid dynamics.